Okay, good morning. Or afternoon, I should say. This is 6:37. Okay, so don't restart your download. I got a call from Professor Bouman, and he's traveling, and so I'm going to be covering today. I just found out over the weekend, so I spent some time reviewing, and hopefully I'll be able to cover this stuff with some adequacy and not require him to correct too much when he comes back on Wednesday. I'm Jordan, so most of you might not know me by face, but you probably know me as the black box that you send emails to get your questions answered. So that's me. So I thought it might be good, since it's a Monday, that I know I took a look through the lecture that Professor Bouman did last Friday, and I know this lecture set kind of contains a lot of these new terms. So I thought maybe it would be worthwhile just to do kind of a quick review on some of the main points before moving forward. So the first thing is, if we go down, is this idea of luminance. I'm just going to cover some of these ideas. So the first one is this idea of luminance, which is essentially, let's go down to this. So the way luminance is defined is in terms of this I function, which is this falls within an integral, but we basically say that we can get light energy by integrating this I function over lambda. So I would really have units of energy per unit wavelength or something like that. And what this concept of luminance is this it's essentially this light energy, but it's weighted by a function, this function y, which describes the visual sensitivity, essentially, of the human visual system to brightness of light. Okay, so we think about this y in terms of this definition as being proportional to energy, proportional to light energy. It's inherently a perceptual thing, though, because it has this weighting factor built into it, and it's kind of difficult to quantify what you mean by units when you're talking about something that's perceptual. But we'll think in here about this y as being proportional to the light energy. So that's a really important point that I know he highlighted, and it's a point that will be used again and again. And one of the important things about that is that if you have luminance from coming from multiple sources, it'll be additive. So this energy is additive. The second point is another concept that was brought up was this idea of contrast, and he talked about this. This kind of experiment where, let's say you have, if you take some region with some luminance YB for background, and you have some dot in the middle of it, and it has some luminance Y. There's an experiment that you can do to determine how different does this luminance need to be from the background for you to just be able to perceive a difference here. So this that's what's known as this delta Y JND, and it's the change in Y. It's this change in luminance where a person can just perceive the difference between these. 50% of the time is the kind of the definition that was given here. And what was found is that if you look at this delta Y, maybe I should put this maybe in parentheses, put JND down here. If you look at this function, YJND, what you find is that this is actually a function of this background luminance. This delta YJND is much, it's much smaller. We can perceive very small changes in luminance if the background illumination is very small. So what was talked about is, what is that relationship? What's that function? And what was described is a couple definitions here. In that, Professor Bouman kind of went through kind of a reasoning experiment. But this can also be verified experimentally, that the just noticeable difference that, in terms of Y if you divide that by the background luminance, that's relatively constant. And that's this idea that's called Weber's law. Maybe it should be called Weber's principle, because it's not necessarily a law that always holds. But for a significant range of the background luminance, this just noticeable contrast that we define, the contrast, I'm sorry, I didn't define it, but the contrast defines this change in luminance divided by the background luminance. This is relatively constant as a function of YB. That's Weber's principle. And then we define, we're going to use this later, we define this contrast sensitivity as being just the reciprocal of that just noticeable contrast. So the relative change in luminance divided by the background luminance, where you can just detect a difference. Okay. I guess that's a good review of that. And lightness. And so what we want to do, let's see. There's another concept called lightness that becomes pretty important. That save that for later. So this concept of lightness was introduced, and it's this idea that the definition is kind of derived with a couple principles we want this to obey. Number one, we want it to be some function of the luminance. Okay, for some function, we want it to be a one-to-one mapping between luminance and this quantity lightness. And the other property we want it to obey is that the just noticeable difference in lightness, we want that to be constant, or very near constant. And so last time we went through a derivation to show that starting from luminance and having something that obeys this property would give you. So this where it is. So this lightness L, the first. All right, the first derivation that he came up with was this relationship: lightness equals the log of the luminance, and it'll obey that property that delta L JND is constant. But this has some very significant problems, in that this function becomes, well, it's not, first of all, it's not defined. This function isn't defined for a luminance of 0. And it's very sensitive to small changes in y if y is small. So it becomes extremely sensitive if y is close to 0. And that's not, definitely not a property we want to have, because having low luminance levels is not that unusual. Okay? So that's a significant problem. So what's done instead, what's typically used instead of that, it's kind of a function that you could maybe argue has a similar shape to that. So this is kind of in theory. In practice, we use the relationship, a power law relationship, L equals y to the p, where p is some number between 0 and 1. Well, I won't say, well, I guess you could. Typically, you're dealing with some number. I'm sorry, I meant p. P is some number between 0 and 1. So you get some sort of a relationship that might look like this. For a different p, it might do something like that. So here's and this is L. And this function behaves much better around 0, so it's much more desirable from that standpoint. And it still approximates this property that the just noticeable change in lightness will be relatively constant over different lightness levels. Okay. And I'll come back to that pretty shortly. So that's probably maybe a good enough review. Let me get to where we're at here. So let's see, he left off here. Okay, so where we're going to go from here is this concept called gamma, which you've dealt with in the lab already. You did a lab that was due, I guess, about 10 days ago. So we're going to talk a little bit now about gamma now that you've seen it in the lab, and maybe we can fill in some of the blanks. Now, this idea of gamma originally came from the hardware technology that was used for video capture and video display. Where it originally came from is, the way that, we used to take videos, the physical device that would capture the light and convert it to some sort of a signal that we could, store, was this thing called a Vidicon Tube. And a Vidicon Tube it's kind of similar to the CRT displays. I mean, there's similarities to a CRT display. It consists of an array of some photoconductive material, and when light hits it, it changes its conductance properties. An electron beam scans across the pattern, and as it scans, the voltage is measured what's coming off that screen. Now, that relationship between the incoming light, which is in units of energy, so that's light energy coming in. The transformation between the light energy coming in and the voltage that's measured at the output of this is not a linear relationship. Okay, and it's well characterized by this function here. So this signal that's coming out, some analog signal comes out and it's digitized. This signal at this point can be related from the input light, I, the light energy, using this relationship. So where this IN just represents the maximum input that can be detected here. At a certain point, it saturates. The relationship between I within the normal range between 0 and IN is given by this power law relationship, and it's described by this parameter gamma I. The relationship between input output is I raised to the 1 over gamma I. Okay, so this x at this point is in this scale. Now, when you want to take this image, whether it's digitized or well, I guess either digitized or it could be stored on analog tape, I guess. But when you want to take that and display it on a device, the devices that were used up until pretty recently were CRT-based devices. Both television and computer monitors, they used the CRT. This kind of device was known to have a similar relationship to this, but kind of basically the inverse. So going from, could you zoom out slightly? So going from, thank you. So going from the digitized image to the output light energy, it was also known to obey a power law relationship, where the exponent associated with that one is this parameter gamma O for output. And I didn't mention, but the 255 here and the 255 here are just assuming that we've encoded this signal using a single byte of information that can get 256 different gray levels. So now, if you want to relate the input light energy coming in and the output light energy that's produced by your display device, you can do it by substituting those two relationships together. So let's see if I can do this. Okay, so basically just by substituting in, we get that the output light is given by that second equation that was shown below, where you have this gamma O relationship, and then substitute in for x using the input energy, using that other gamma I relationship. And just simplifying that, you get that the output light energy is going to be equal to the input light energy raised to this factor gamma O divided by gamma I. Okay, now if those gammas happen to be equal, if they were the same, then these would be linearly proportional. And in that situation, we say that x is that encoded representation for x is said to be gamma corrected. In other words, if those two gammas happen to be the same, the representation for x here has basically the inverse relationship for this, so that even though this value here isn't in the units of light energy, when it goes through the transformation of the CRT, it'll represent light energy. So what needs to be done is if you have an image that's encoded, and this is what you were doing in the lab, if you have an image that's encoded using a particular that's encoded with a particular gamma, and your output display device has a different gamma, you have to run it through a transformation that looks somewhat like this. Okay, and so that's where gamma originally came from. Now, a very good question is, why do we care about it anymore? Because we're not using CRT. Nobody's using CRTs anymore, right? Everybody's got a computer in front of them. You can't buy or sell a CRT these days, I don't think. You can't give them away, it seems. And also the digital cameras, video cameras, they generally don't use Vidicon tubes either. They've been replaced by CCD arrays. So since that technology isn't being used anymore, how come we're doing a lab where we're doing gamma correction? Why do we have to do gamma correction before we display an image on a digital monitor? If you have a digital monitor, there's no physical reason that it needs to obey this relationship, right? Because the output light that's produced by a monitor, this mapping going between the input encoded value to the output light is basically controlled by a lookup table. So you could really the monitor could apply any transformation at once. So one thought is that one possible reason you might think is that, well, these digital monitors have been slowly replacing CRT monitors, and so we have all these digital images floating around that are all in this gamma corrected format. And so in order for a digital monitor to display the image the same as a CRT monitor would, it needs to go through a gamma transformation. But as it turns out, there's another reason that's actually very important, and that comes about where if you notice that this relationship that's shown, this property of the Vidicon tube, you can see that is very similar to this power law relationship that was introduced before, where this power law relationship the purpose of it was to put this Y transform it into a perceptually uniform space, in the sense that if you look at changes in, if you look at increments, uniformly spaced increments in the L direction, the change in contrast that you see between these levels will be equivalent, roughly. They'll be close. They'll be relatively close together. Now, so what that means is if you want to, let's say, you want to encode this image, like here it's even written on here that this image has been digitized. If you want to encode this image, you're going to want to have your quantization steps between the different levels of this value be imperceptible in terms of its the change in luminance that it produces when you look at it when you look at it on a display device. If that increment between the encoded values is larger, that's going to be very visible in an image. We're going to basically see what are called false contours. So if you look at this scale, this sort of a scaling is very useful if we for the encoding process. If we want to digitize this, if we want to quantize it to using some uniform a quantizer that uses uniform steps. It's much better to do it in this scale, because if we wanted to do it, if we tried to apply that scaling in the luminance direction, and we had this condition where our step size needed to be small enough to where we can't perceive the change in luminance, that means we would have to design the system. We would have to set that quantization step size to be very small, because at low luminance levels we're very sensitive to small changes in luminance. So we'd have to use a really small step size all throughout here, and that would be very inefficient, because all these step sizes up here in the high luminance levels, we can't perceive them anyway. So there's no reason we have to allocate bits to encode all these different steps up here. So the easy thing to do is to run it through a transformation, and effectively what you're doing is you're stretching out the luminance in the lower range. I'm sorry, you're compressing the luminance in the low range, and you're stretching it out in the high range. So, if you map these uniform steps in the L direction, you're going to see them concentrated very highly in low luminance levels, and it'll be spaced further apart as you get higher. And it just happened that the hardware applied a transformation where it essentially had that effect. And so the encoding here could be done very efficiently in that respect. So that's the main reason that gamma is still around and it will stay around. It's for encoding efficiency. There's no reason to allocate a uniform quantization in the luminance direction, because what we're really interested in are differences in contrast. Okay. So let's see, where are we? Okay. Oh, another thing I wanted to mention about that is maybe some of you might have noticed in the laboratory that you did over gamma correction, you were given an image that you were told was encoded in a linear scale, and you had to apply a gamma correction so that your display would display it correctly. And when you viewed the image that was ungamma corrected, it looked dark, because essentially the monitor, the display device has a response that essentially goes like this, where here your encoded value is along this axis, and this is the corresponding luminance that's produced by the pixels. The monitor effectively has this response, and so it appears too dark because everything is being shifted down in terms of luminance. Well, when you apply the D-gamma transformation, essentially you run it through a transformation like this to undo this display, the monitor's response. If you look closely at that image after you ran it through this transformation, and a couple students asked me a question about this, so some people did notice this. There are certain regions of the image that are dark, and if you look closely, you see what looks like some garbage in there. It looks like you have some kind of a weird distortion occurring, and what you're seeing is those false contours that I mentioned around in those dark regions, essentially. The pixels that are, say, I don't know, I didn't look specifically at the values, but that are between 0 and 5, you're able to see those step sizes very clearly. They're very perceptible. And so that distortion that you're seeing is the exact reason that you don't encode an image pixel value in a linear scale. That's the exact reason why it's not done, is because of that distortion you see. Okay, so I just wanted to relate that, because no mention was made of that no mentions made in the lab document about that effect, and it might not be something you notice unless you look really closely at the output image. So it might be worthwhile going back and looking to see if you can see what I'm talking about. Okay, so what we've been covering up to this point is how the human visual system can perceive differences in luminance. And so what we're going to talk about now a little bit is how the human visual system responds to changes in luminance as a function of space. Okay. Right now we've only been talking about changes in the value, the brightness value, but we haven't been talking about any spatial characteristics. And so the common characterization of that is this thing called the MTF, which stands for modulation transfer function. It's essentially a frequency response, a spatial frequency response of the human visual system. And so how might you measure that? Well, here's one idea for an experimental setup. What you can do is produce a spatially varying pattern. In the simple case, just a sinusoid, a sinusoidally varying light intensity as a function of position. So here it varies as a function of x. So specifically here it would look something like. Let me draw a picture of this function. Okay, so this function that's drawn, I'll just draw a kind of quick picture of this. So actually, maybe I should have scaled it up a little bit. Okay, so it's a sinusoid that has an offset of yb, and it has it varies. The luminance varies sinusoidally, and the peak-to-peak value of this variation is this delta y. So it might look something like this. If we were to look at like one slice through that picture. Okay, so this difference here is the delta y, and yb represents the background luminance. Okay, and the units along this direction are, well, this is varying with space, so I'll call this x. This will have units of inches. Okay, and the period of this sinusoid will be 1 over f0 here. Okay, and that has units of inches as well. Okay, so we produce this pattern. Luminance changes by delta y, and the spatial frequency, how fast it's varying, depends on that f naught. So this. So I guess it wasn't mentioned. So this f naught, that frequency that we have up here, this f naught, is in units of cycles per inch, because our independent variable here is x represents a distance in units of inches. These units don't end up being so useful for modeling the human visual system, because how fast this is varying in cycles per inch there will be a dramatic difference in how the human visual system responds to that, depending upon how far away this is. So the better units to use for this dimension is, rather than using inches, spatial inches, we can kind of get rid of this effect of how far away it is by instead looking at units of the change in angle in our visual field between between these bands here. So the more common units to use are angle in degrees of our visual field, and the spatial frequency, rather than doing cycles per inch, represented in units of cycles per degree. And so this is kind of a quick derivation. I can do kind of a quick derivation here. Let's see if I can find it. So I'll sort of redraw that a little bit. So we have this. So let's say we have this board that has this pattern here, and there's the I. That's a distance of d units away, and we have some small distance here, which represents some little. So this is an x direction. I've drawn it vertically, but So this is, let's call this delta x, which represents the spatial period of that sinusoid measured in cycles per inch. Okay, what we want to do is we want to convert that into degrees, units of degrees in our visual field. So marker's kind of thick. So this angle here, let's call it phi. Okay. And let's see, let me move this over here. Okay, the expression that's given in the notes there uses a couple approximations. So we have the relationship that delta x over d is going to be approximately the sine of that angle. If d is much bigger than delta x, this is a pretty close approximation. And another approximation you can make if phi is small is this is going to be approximately equal to just phi, because sine has a slope 1 around phi equals 0. So I'll say for small angles. Okay, so the delta x is going to be approximately equal to d times phi times, this is if phi is in radians, so let's convert it to degrees, because I said we're going to do degrees. I said we were going to use units of cycles per degree, so let's put in a factor 180 divided by pi, and this will be units of degrees. Okay, so using this relationship, if we can define this new spatial frequency, I'll call f naught tilde, in cycles per degree, as 1 over phi. We take 1 cycle per degree, and it gives us the conversion. So we have just substituting in up here, we have d over delta x times 180 over pi, which equals df naught times 180 over pi. Okay. And that's the expression that's given. Oh wait, no. What did I do? I didn't invert that. I messed up somewhere. What did I do? Yeah, it should be. This should be right? We're gonna screw up.
Invert the phi, so
What?
we invert the phi, and the phi is pi over 180.
That's consistent with this, though, isn't it? Well, this would be. Let me see. Oh, I'm sorry, because this has to carry along with the phi too, because this is the conversion for the angle. Yeah, I'm sorry. Yeah. Well, anyway. Yeah. I'm sorry about that. So this factor here should be pi over 180. Yeah, I needed to carry that along with the phi when I moved it over, because it's just the sign. It's just the unit conversion for the angle. Okay, so it's consistent anyway. I just thought I'd go through that. So that's where this is coming from. It's using a couple approximation. It's using a small angle approximation for both in two places. Okay, so let's see. Where do we want to go from here? This is a mess. Okay, so what we can do, you can do an experiment where you measure how a person responds, how a person can perceive a variation here. How, you can measure by varying the spatial frequency and the delta y in the background, or you could hold this constant or you could change it. Measure what's a perceived response, and there's kind of a let me first show an example of. So this is a figure. I don't know how well this plot is a little bit noisy, so I don't know if you can see the printout was a little bit noisy, so I don't know if you can see the effect very well. But this is an example of something where what we've done here is, from this equation, we're varying the spatial frequency of that sinusoid along this axis, and we're varying the contrast as we go up. Here, this background YB is held constant, and we change delta y. We make this delta y, we make that sinusoidal variation smaller and smaller as we go up. And I don't know if you can see it too well. I can see it actually better on the display than I can on the printout. But you can perceive kind of an envelope to this thing. So at higher, what happens is at higher frequencies, in order to be able to resolve those bands, you have to increase the contrast, which you have down in this range. So you can kind of, in a way, you can kind of see that response. So that function that you get by measuring the response of the human visual system, measuring its contrast sensitivity as a function of spatial frequency, measured in cycles per degree, you get a shape that looks something like this. It has basically a bandpass response. You have this low frequency cutoff where all these represent, this range down here represents very slow variations, very gradual variations. And this response, if you believe it, this is kind of this is what Professor Bouman calls a factoid. This figure wasn't generated by doing perceptual experiments. This is just this is a trend that we observe, but this isn't determined. This particular figure isn't determined scientifically. But there is this effect down at very low spatial frequencies where we become less sensitive to it, and this is intuitively what it means is when you have these very slow variations in gray level, it can be difficult to perceive. It also ends up being a very difficult thing to quantify, because there's another aspect to this in that our eyes generally, normally aren't fixed at one position. Your eyes kind of move around at random, and there's an effect that does have an effect on how it responds to these low variations. So this is not, this might be a response that you'd see if you were somehow able to fix somebody's eyesight right on a particular point, which is not necessarily that easy to do. But this is something that has sort of a temporal component too. So this portion here is kind of difficult to quantify. It also ends up not being very important from an engineering standpoint because this actually occupies a very small band of frequencies down here, and so it doesn't end up being very useful to exploit this effect in your imaging systems. So usually this is in imaging systems most often this portion of the response isn't taken into account. And so, so the other aspect of this contrast sensitivity function is that it's relatively flat within a range, and then you have this high cutoff frequency that occurs where your response starts to roll off. Your contrast sensitivity starts to roll off as the frequency increases, and that roll-off starts to occur at approximately somewhere around 10 cycles per degree in your visual field. This portion of the graph is very important when you're designing imaging systems, and you can exploit this very well. There's a couple applications where this section becomes very important in when you design imaging systems. One is coding, what you're going to do at the very last lab. This is essentially what we're talking about is image compression. you know. And you're going to, at the last lab of the semester, you're going to have a really grand old time designing an actual JPEG encoder. You'll have a lot of fun with that, I'm sure. But it's kind of cool. You're actually going to go through all the steps to do that and produce a file that you'll actually be able to read with a regular image viewer. Anyway, this response becomes very important in coding, because what this is saying is that the human visual system becomes less sensitive to higher spatial frequencies. What that means is when you want to encode an image, there's certain information in that image that you might be able to throw away. And in throwing it away, the person viewing, the reconstructed image won't be able to see a difference. Okay, so you can exploit that to compress an image greatly by throwing away information that isn't very easily perceived. And another application that you're also going to be doing in lab, I think it's the second to last lab in here, is halftoning. And halftoning is an application where maybe Professor Bouman's probably mentioned this up to this point. If you're not familiar with it, halftoning is it's an application where you represent gray levels with some rendering device that can only output black and white. Okay, so a printer is an example of something like that. Printers. If you're talking about an inkjet printer, it can, at a particular point in an image, it can either produce a dot of ink or not. It can't produce those subtle gray levels. So what's done is you produce patterns of black and white to make it so that when you look at it from, a moderate distance, assuming these dots are spaced relatively close together, it will appear as gray, because what this response up here is effectively saying is that your visual system is going to blur at these higher spatial frequencies. So the image will, in a region where you have this sort of a dot pattern, it will be perceived as a gray level, even though if you look at it closely, hold the paper right up to your face, you'll be able to resolve the individual dots, individual black and white regions. So you're going to have some experience. You're going to do an exercise with that too, which is kind of neat. Yeah, so in both those cases, this portion of the response becomes very important. So it's important to have that well modeled. Okay, so as we design imaging systems to kind of exploit these things, we're going to have to somehow quantify. We're going to have to quantify that response. So that gets into this idea of fidelity metrics. And what we say by image fidelity, what we mean by image fidelity, is it's some quantitative representation of the difference between some underlying, like, gold standard image and the image coming out of your imaging system. Generally it's a measure of how similar, how faithfully reproduced an image is to the original, and it brings into account perceptual effects. So it brings into account, this bandpass characteristic of the human visual system, for example. So those are incorporated into this, and the differences between the images when using this fidelity metric are typically right around the just noticeable levels. Okay. And we're going to talk a little bit about that, and you're actually going to use that metric when you do that halftoning lab, or you're going to use a similar metric when you do the halftoning lab. These other ideas of similarity and quality are quite different. Similarity is also a measure of the difference between two images, but there's more of a subjective quality to that. In this case, the differences are way above the just noticeable difference level. So you're actually dealing with two different images. I mean, two really different images in terms of what they contain. An example of what we mean here is if you have, two images of an automobile. Okay, there are two different models, and they're two completely different pictures. A person would look at those and say that these are similar. These have some similarity relative to a picture of a car and a picture of a face, right? So there is some kind of a metric, but it's very subjective. And it's not. It can be difficult to quantify, but it is very important when in image database applications, where, for example, if you have a database of a bunch of face images and you want to try to do face recognition, given some picture of somebody's face, well, you're not going to have the same exact picture. It might be at a slightly different angle. The person might be smiling. Maybe you didn't shave that morning. But you still, need to design a system to where you can try to determine, similarity between that image and the images in your database. And this last idea, this other concept you list here on image quality, this is something that's very difficult to quantify because it's completely subjective. And it really is just simply how pleasing an image is to the viewer. It doesn't have anything to do with how accurate the representation is. It's completely subjective. While it's very difficult to quantify, it's still something that you might have to consider when designing an imaging system if you want your customers to buy it. You want your customer to have a positive emotional response when they look at the output of your image. So this does have to come into play, sometimes if you're designing a system that you want a lot of people to buy. What's going to be most important for us is this idea of fidelity, that fidelity metric, that first idea. Now, this is a typical. Could you zoom in slightly? Maybe that's good. I'm looking at a very small display, so I don't know if it registers better if you can see it better on your monitor. So this is a typical system. This is a very simple idea of measuring the fidelity, measuring the difference between two images. How closely these the two images coming in match. Now, there's a couple things going on. So let me we only have a few minutes, so I'm going to be I'll be a little bit brief in describing this. But these filters are approximating that basically this response of the human visual system. It's a low-pass filter that is sort of modeling that response. So there's kind of a strong assumption is being made that the human visual system behaves as a linear time invariant system. But it ends up, while it's a pretty strong assumption, it's not necessarily a bad one. Now, so what this represents is basically, it's a low-pass filter. You think about an FIR response. It's a weighted average of pixel values in some window around, a particular point in the image. Now, in doing that weighted sum of pixel values, in order for that to really make sense, the units of those pixel values should be light energy, right? For the same reason Professor Bouman was emphasizing last time. When you're combining light sources, they're additive in energy. So you want the units of what you're putting into this low-pass filter to be units of energy. Okay, so you want them to be in a linear scale. So linear in the sense, linear in energy. Oh, I missed a couple letters there, but that should be energy. So if you're starting out with images that are in a gamma-corrected format, which they very may could be if you're just pulling them off the web, for example, you need to de-gamma them. You need to put them in a linear scale before applying this low-pass filter. Otherwise, that weighted sum won't make sense. Okay, so that much makes sense. Now, what about this raising to the 1/3? I mean, why don't we just take these images and just take the difference of what's coming out of these low-pass filters and just sum up the squared difference? We have this. It seems like we de-gammaed and then now we're like re-gamma correcting again. Does anybody have an idea? I know you have an idea. I know you know well. But the reason is because think about an image. It could contain both light regions and dark regions. And we want to quantify differences between these two images in both those ranges. Now, what's most important in looking at the difference between images is what can we perceive. So what we're really interested in is the contrast. And remember that the contrast is different in, the just noticeable difference in the light regions and dark regions is different. So if we do this mapping, if we put it in that perceptually uniform scale, then the differences we see in dark regions and light regions will be treated, similarly. We'll be putting those roughly in the same scale that when we look at the total difference between the images, we're getting something that's a pretty good representation of the difference, the pixel-wise difference. So that's about it. Music should be starting, and so I hope that makes sense, and Professor Bouman can correct anything that I left out, or hopefully nothing was wrong. But so good luck, and he should be back on Wednesday.